homework number, no, but the number 8, homework number 8. Problem number 14. All right, it was the Ferris wheel one, where the Ferris wheel is in these different positions. And there's asking about several different things. All right, the key thing is to draw your free body diagram properly. At the bottom, oh, by the way, since it's a Ferris wheel, it keeps the same velocity or angular velocity the entire time, right?
Yes.
Okay, different than the ball on the string where it speeds up, or a roller coaster where it speeds up on the way down, slows down on the way up. Okay, right here, it doesn't really matter which way it's rotating. It could be clockwise or counterclockwise. It's really irrelevant. What we have is we have mg, we have mg, we have mg at each spot. Just because you're in a Ferris wheel doesn't change the Earth. That stays the same each time. But what does change is our tension or force from the Ferris wheel. The force from the Ferris wheel is up this way, down over here, and inward over here. Okay? So at the bottom, I think everybody did pretty well here. You're accelerating up, your acceleration is up here, and your acceleration is down here, so most people got this right at the bottom. F minus mg equals mv squared over r, or omega squared r, right? That's not a big deal. At the top, you get F plus mg equals mv squared over r, or m omega squared r, whichever one, right? Over here, this is where people were having trouble. It asks for the force from, what, the Ferris wheel or the seat on the person or whatever it was, something like that. Is that right? Okay, the deal is that a lot of people were just assuming that the normal force was mg. But it wasn't.
That's what it was for a lot, for most of that. It was for a lot.
Well, you got lucky because that's wrong. This force must have been so small that it didn't matter, because that's incorrect, actually.
Was the problem wrong?
The problem may have been wrong on the E homework.
I used mg squared over.
Because it should have been this. There are two forces. There's mg here, and there's this force here, but this force here is mv squared over r, or m omega squared r.
Triangle.
So what you have to do is you have to put these two together to find the total net force. And so your total net force is going to be mv squared over r squared plus mg squared square root, because you have to Pythagorize it to find the total. Right? So, those of you that just got away with mg, I don't know what the deal was. Yes. Did you get away with mg? How many of you got away with just mg? There is a mistake in the key.
I think you should dock some points, you know.
No, I did mg squared over r.
Because I went through the trouble of doing all that.
You should add 10 points everyone.
Okay, the answer is...
Everyone.
Oh, I know why some of you got away with just mg.
Why?
Here is why. Because... Oh, wait a minute, hang on. Let me make sure I got it right. Yeah, I think I know why some of you got away with it. Because here's the deal. It does show in the answer key that you have to have the centripetal acceleration squared plus g squared square root, then you multiply it by m. They factored the m out, okay? But since g is 9.8, or approximately 10, if your centripetal acceleration was small enough, then you may have gotten in within the 1% error.
Yeah.
Wow.
I think is what happened.
I did mg squared over r either way, so I'm good.
I think that's what happened, is you got within the 1% error, and so, especially since it was squared, right? So if your centripetal acceleration is 1, but g is 10, when you square it, you get 100 plus 1, and you're within 1%, right? So I think that's what happened. For those of you that are clapping right now, you cheated.
Cheaters.
We didn't cheat. We didn't know we were cheating.
Cheaters never win.
So it's okay.
We didn't know.
Yes. If your centripetal acceleration is not significant enough, then it won't matter. And let me ask you this. What?
On
on one homework, someone accidentally put in the answer 1 up and they still got it right. So each homework is really screwed up.
1 up.
Wasn't that you said?
You mean like-
9, they answered 8.
On multiple choice?
No.
They
On
had,
free
they had like
response.
the answer to number 8, they worked number 8, and then they accidentally put it in number 9, and so got just typed answer.
That's weird because I mean, if I even do that,
But that's
in
me-
one.
Well, I'm glad to see that e-homework is becoming a random number generator.
I did that on chem skills one time.
Wow.
Put in a random number when I didn't know what it was, and it was right. That
They
happens
haven't.
a lot.
They have it in Kim
Don't,
skills,
don't
though.
say that on.
Ah.
I
All
worked
right.
through the problem. and
On
it
a
helped
real
me
Ferris
understand
wheel,
the
would you
topic.
expect the centripetal acceleration to cause much of an effect over here on the side? Okay, in a real Ferris wheel, we're talking it's slow, right? So your centripetal acceleration ought to be kind of small. So in the real world, that may be true as well. It may only account for around 1% of the force.
We were thinking real quick.
Yeah, we're thinking real world. Like MG looks good to me. All right. So I got emails on that one. That was the one that I think most people had trouble with. Apparently because some of you were getting by with it and others weren't.
Yeah, well, there was a lot of confusion.
It's not
Yes,
fair
there
that
was
they
a lot of
get it right here,
confusion.
and I'm not.
So some of you paid the penalty. All right, I had some homework.
I think the homework decides on who to take on once in a while.
I asked you to turn this problem in, or I asked you to do this 2 times ago. Turn it in now. The one that I drew on the board.
I don't know if it's right.
The one with the 40 kilogram weight.
Mine's attached to my
So
notebook.
it's on the back of this. Okay.
Mine's on the back too. So was mine.
I just did.
All right, hang on. If you did it on the back of your orange paper, hold up. Let's talk about the ones on the orange paper first. All right, everybody got your orange paper like me. Orange. Orange.
Like Michael.
Okay, number 13. Come on.
We don't
All right,
need to
if you
go
can
and
do
that.
this-
Put it in the calculator.
Quiet. Quiet, quiet. If you can do these next couple of problems, you're probably going to be in really good shape for torque where you have an object in static equilibrium. Now remember, in static equilibrium, the sum of the forces in the x equals 0. Do we care about pivot point for this one? No, we don't care. It's just the forces in the x direction. All right, the sum of the forces in the y must equal 0. Once again, no pivot point, just vertical forces. And then, our new one, sum of the torques equals 0. For here, we must pick a pivot point. So I'm going to draw a little dot down here. You must pick a pivot point. Okay? That's important. And you can pick your pivot point anywhere. So I'm going to put
So which one are we doing, 13?
anywhere you can pick your pivot point. And where we pick our pivot point is what helps us solve this problem. Okay? Because we cannot solve it otherwise. All right, all the forces that act on this object, there are. There's an mg here.
I got that.
There's an mg at the center of mass. We're going to talk about center of mass today. Mg here. There is a tension this way. Now this tension is at 1, 2, 3, 4, there's 5, 6, 7, 8, 9, 10. Wow, look at that. Very good. All right, and we have a horizontal and a vertical force
Yes.
right here. Now technically in the real world there's just one reactionary force.
Right.
So they may, on the test, say, what is the direction or what is the magnitude of the force at the wall? Or they might say, what's the direction of the force, reactionary force at the wall, or something like that. Now what we're doing is we're finding the horizontal and vertical components because it's easier for us to think of them that way. But really, we add those up to find the result. Does that make sense?
Yes.
All right. So, right here at the wall,
It has to be horizontal.
do we know which way they have to be, the horizontal and vertical?
No, horizontal has to be
Okay, we know horizontal has to be that way. Do you have an idea which way vertical is?
down. All the way down.
It depends on how much that thing is.
Down.
Yeah,
it is
it maybe
down.
has to go.
Down?
Down. Where's the pivot point?
It doesn't.
Right? It doesn't matter where the pivot point is. That force is going to be irrelevant in where the pivot point is, since it's not rotating.
But you can't have the pivot on the left if you're trying to.
Now the real pivot point is right here, okay? But it's not rotating. We have a lot of you saying down, and that seems very counterintuitive. So let's figure this out, okay? Let's write our three equations. The sum of the forces in the x equals 0. Write this one. The sum of the forces in the y equals 0. Write this one. And the sum of the torques equals 0. Write this one. And you need to pick a convenient and nice pivot point.
It has to go left, otherwise it will fly off the wall.
Okay, now x and y we ought to be able to do right off the bat. It shouldn't take us too much time. Okay, we got a horizontal, we got a vertical, 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 and we got both. So right here, we got to split this up. Now they did not give us an angle, correct?
Correct.
So I'm just going to call this part over here Tx and Ty, okay? Since we do not have the angle.
Texas.
That's right.
Were you not here last time?
So in the x direction, we know that Tx equals h. Bingo. Done. This one equals this one. All right, in the y direction, we have this. That we have Ty, the way we've drawn it, Ty up equals v plus 2mg. That's the way we've drawn it. Now, this equation does not definitively prove whether v is up or down.
Right.
Because it could be on either side of the equation, and this equation would make sense, right? It really doesn't matter. Okay, so we need to pick a good pivot point for us to decide which way v really is, the vertical component. Okay? So where do you want to pick your pivot point?
At the center.
At
Yeah.
the center. Center mass.
Really?
At tension.
That would eliminate
Or
At
at
the
the
wall.
tension.
I don't know.
I mean, if we're just like trying to determine which way V goes, but at tension.
Oh, at tension, because then you get rid of no,
But in this you have weird angles for MGs anyway.
Yeah.
So
We may have to put an angle in here just to help us out. You know what? I pick this point.
Why? But that gets rid of V.
Hey, sit at the wall. Cool.
I'll show you why. I pick this point. Now, a lot of you pick this point, and you can work it that way if you'd like. You will be able to figure it out from that, I think, eventually. But your equations end up being larger, and more complicated. I pick this point, and the reason why I pick this point is it's going to eliminate these two.
But don't you
And-
want to know where V goes?
It's going to show me my relationship between these three. Okay? All right, I think I'm going to have to write an angle in here somewhere. So let's choose an angle. You want to choose this angle as theta? Okay, if that's theta, then that's theta, and then that's theta here. Okay, where's theta over in here?
There is no. Well,
Yeah, there is. Somewhere.
Is it below? Like the little dotted.
Here?
No,
right
above.
Here?
Yes.
Here.
Yeah.
No.
Wouldn't that be it?
I hate angles.
Oh,
Ah.
yeah, the,
I think it's
it's
Okay.
under the dotted thing, I think.
Yeah.
Is-
This
yeah.
line and this line are parallel, right?
Oh my god, I'm gonna cry.
Yes. Yes, they are.
This line bisects them, so I've got
I
this
saw
one
some angle.
and this one and this, right? So this is theta and this is
Oh my
theta,
God.
right?
oh.
So that's theta.
Yes.
If that's theta and that's 90, then what's that? So what's that?
Theta.
Oh my
Theta.
God.
We've done it.
I don't think we did it alone, no.
Can we not do that again?
You must do that. You got one of those on your e-homework tonight.
Oh.
You might have two on your e-homework.
Three, actually.
3.
It's actually a circle to line.
All right.
I say that angle only does 45, so that way we can 45, 45,
So,
90.
and I've got
So
two
Mr.
of them wrong.
When you're doing why, you just always make me positive.
Why did we pick it down instead of up? See, we don't really know for sure which way V is. We can tell for sure H is to the left because it has to balance this out, right? But we don't really know. We have quite a few students saying it has to be down. We're finding out. I drew it down just because that's our guess.
But it doesn't matter what it's up or down.
No, when we solve this, if this turns out to give us a negative answer for V, that means we picked our direction wrong over here. Okay?
So should we use an X then torque then?
Oh, God.
Maybe. But I'm going to do this.
That's fine.
Okay, here we go, everybody. I want you to write the torque equation right here about my pivot point. Go.
Okay, that's not
Was it
horrible.
here last time?
We'll call it. It's all of
Come on, you got 30 seconds.
3T.
Yeah, 3T.
3T. Now, wait a minute. Is this torque, is that a positive or negative torque for this one?
Positive.
That's a positive torque, and these are going to be negative torques, right?
Yes.
Okay, so this one is on one side of the equation, these are on the other side of the equation since we have it, they equal 0, right?
3T equals
Okay, so 3T equals what?
5
sine theta
5 mg.
5 mg
sine theta
sine theta.
plus
10
10.
mg sine theta.
Okay,
Wait, why is it, where's all
So it's
this?
just
Wait, this is the
15
torque
mg.
equation.
Oh,
okay.
T
Why does T not have a theta?
is perpendicular.
Because the radius is right here. Here's my radius. My radius is 3. The angle is 90. So it's sine of 90. Right? So it's 3T sine of 90. All right. Over here, what most of you are doing, I think, torque is RF perpendicular. And you're finding the perpendicular part of this force, right?
Yes.
And the perpendicular part of the force is right here. So you're using sine theta. That works out. So what you did here was RF perpendicular. This is my perpendicular part of the force. And R times F perpendicular. Okay, excellent.
Okay, that makes more sense.
Does that make more sense? Now remember, when we're finding torque, we have R cross F, RF sine theta, RF perpendicular, or R perpendicular times F. Any one of those is the same statement, right? And for us, the radius times the perpendicular part of the force seems to make the most sense to us, right? It seems to be the easiest for most of us. So that's why we used this, because a lot of times picking out that angle is not the easiest thing to do, although for us, you notice that our radius is going out this way. And so, oops, I wrote that wrong. And so this is the proper theta to use anyway, right? Okay. But sometimes when you're finding your perpendicular part of your force, you'll use cosine to find the perpendicular part of the force to the radius, okay? So you're just finding the perpendicular part of the radius. All right, so this is equal to 3T equals 15 mg sine theta. So what is that? T equals 5 mg sine theta.
I'll figure it out.
All right, so T equals 5 mg sine theta.
That's
3T. Where did the 3 go?
All right, so if that's T, what's the vertical part?
distance. It's 3.
5 mg sine squared.
This is 5 mg sine squared theta.
The other forces are making
And
it
so
together.
that's
Wait, I don't know.
And since we're not moving, the torques have to
Oh,
equal,
he's just
right?
Yeah. Wait, what?
Right?
Hold on. I mean, I know what you're saying. I just don't know what you're saying.
What do you mean?
Like,
Do you see this picture?
So how does that help you?
Oh, he's solving for
yeah, but
In
it
direction.
Hang on.
5 mg sine theta.
All right, so here we go.
Perpendicular
Does everybody see that these are correct? Are these correct?
Yes.
I did leave.
Yes.
All right. So that means that that H equals 5 mg sine theta cosine theta. Is there any trig identity that's going to help us out here?
Yes, you would.
That's sine 2 theta?
Actually, like 2 sine theta cosine theta.
Oh yeah, 5 mg sine.
No,
That's sine 2 theta, right?
yeah.
Huh? But
Well, no, 2 sine.
Oh, this is crazy.
2 sine theta cosine theta is sine 2 theta.
Oh.
So you can do like 5 over, yeah.
Oh my god.
Yeah.
Yay.
You know what? We do not have to go this
I know,
far.
it's-
Okay, good.
That makes us sad.
Yes.
I've been
And
sad.
remember, mathematically, this and this is the same anyway, right? But that's the
I got that now.
2 sine.
That's the overachiever.
Yes. If we're on our
After that-
test, this is far enough.
Because it's just cosine dividing it into more.
Right.
To the
So
two.
why is it
But
sine,
like,
cosine?
I see this 3
Because this is equal to 5 mg sine theta.
How does that go to 2 equals 5?
He divided by 3.
And then to find the x and y components, I have to find the cosine and the sine part of that.
Okay,
Oh.
I see it.
Ah.
Hey, wait.
Oh, what happened to 10 mg sine?
You added
Added them.
Oh.
Got it.
Right? Now that's unusual. We're not used to seeing that, right?
I don't believe anymore.
No, we're not.
You don't
Okay.
believe anymore.
Now, let's go over here.
Not physics at least.
Ty then is actually 5 mg sine squared theta equals v plus 2 mg.
Yes. Oh, that's true.
Okay?
Okay, see that.
And we say MGs.
And so v equals 5 mg sine squared theta minus 2 mg, or that v equals mg 5 sine squared theta minus 2.
And that,
Okay, tell me,
do it cosine squared.
what?
This is for
No.
me saying that it actually wasn't that.
Okay, tell me, under what conditions is this positive?
Yeah.
Yeah.
When it's greater than positive 2.
Alright,
When sine squared 5 sine squared theta is
sine squared theta has to be greater than
2.
2/5.
Which means it has to be greater than root.
I don't want to.
arc sine theta has to be
I don't want to.
more than
Sure you can. Real quick, graph sine squared theta and graph 2/5.
what?
See? Can you see?
Yeah, it's gonna be
Theta can be negative for fun.
Alright. Notice that sine squared theta is always positive, right? Okay, sine squared theta is always positive. Notice that it does drop below the 2/5 line, right? Alright, multiple times, or depending on what the angle is. Now remember, our angle is only going to be...
less than 90.
You see it?
I'm so glad I have theater to contradict.
Right here. Alright, when you graph that, make your window for x, which is going to be our angle, correct?
Yeah.
Make it between 0 and 90 degrees, which is going to be what? Pi over 2,
I think
which...
that's in
What are we
degrees.
doing?
This is in degrees? Nice, 90.
What are we doing?
The window.
Oh, okay.
We want to do things in degrees.
So there you go, it looks like this. Then it will look like this.
We could find an intersection.
4.
Alright,
Okay, square root.
so at what angles theta are we going to get too small?
The arc sine of root.
When we get, oh shoot,
We're gonna do the simple way to do it.
trace, no,
Second.
calc,
Second trace.
intersect,
Okay.
Bianca and Hertz.
yeah, Okay, I show 39 degrees.
Yes.
Okay, it's 39 degrees. If you're under 39 degrees,
That's what I got.
if this angle here is under 39 degrees, then V will be upward. If you're over 39 degrees, then V will be downward, like we expected. Because then,
Oh, yeah.
when you're at 39 degrees, then sine 39, thank you, sine squared theta at 39 degrees is equal to about 2/5. When you're under that, when you're under 39 degrees, then it will be less than 2/5 and V will be negative. That means V will be in the opposite direction we pointed it. Does that make sense?
I don't understand
So
why.
therefore, at 39 degrees, what happens?
Where are we getting?
At 39 degrees, oh, good question. At 39 degrees, what's my vertical force?
Not there.
0. It will be nothing. It will not need to exist.
Okay.
Or will it?
Like, why is 2/5 so?
Because at 39 degrees, this Ty and the 2mg will be equal.
Define as existing.
Where do you get 2/5?
Out of existence.
That's
All right, we had questions. All right, Andy, what's your question? Your question is,
How did we get?
Oh, okay, so you're setting 5 sine 2 theta, okay. I
got it? All right, 39 degrees is our break point. So if this was at 45 degrees, then we would have drawn V in the right direction.
Oh, southwest.
Okay. Anything over 39, and we drew it in the right
It will be in
direction.
the
Yes,
way
ma'am.
further notices.
What if the masses aren't the same? Okay, if the masses aren't the same, then we have something other than 2m here, and we have something other than this here, and it changes up what this answer here is going to be.
But you can still find.
But you can still find it. All the physics that we have here is the same. What you would just do here would be, this would be M1 and M2. And so they wouldn't combine like we have here, and our problem would be a little more complicated, but we could still solve it. Okay?
That's dependent on tension being.
And that's correct. We are also assuming that if we change our angle, theta, that our tension is remaining perpendicular. So you can see that it can get really complicated if that
Like
doesn't
if I had
become
a set
perpendicular.
place on the
Yes.
ceiling.
Yes. Right. And then you have to have, a little tier. Because then you have to figure out the function for what that angle's going to be. Very good. Excuse me. All right. I don't believe any of the ones in the homework that I gave you are quite this complicated.
You said they were me.
And the thing is this, though. Like, for instance, number 13. Okay, 13 is actually not as hard as this one. It's kind of similar. You have a weight, you have a perpendicular tension, and you have a reactionary force on the ground. You can actually pretty quickly tell which way the horizontal and vertical components are. But look, everybody. Okay? Let's just do this. Let me just look at 13 real quick and show you what you do if you pick the wrong direction. Number 13 looks like this. We have a tension this way. We have an mg this way. And we have a pivot point here. It's the boom and cable. Now look. Does the boom have a weight?
Yes.
Yes, it does. So we have another mg here. I'm going to call this M1G and M2G. All right, M1G and M2G because they're not the same. Now look, right here. They're going to want to know what the horizontal and vertical components of the force are right here. You know what? I don't know what they are. So I'm going to pick some random directions. I'm going to pick this direction. I'm going to pick this direction. Okay? Does it matter that I picked them that way?
No.
Let's say I wasn't thinking ahead, and that's what I picked. Because, you know what? That horizontal is definitely wrong. Because tension's pulling it to the left. My horizontal force is pulling it to the left. That means it's going to accelerate to the left. Okay? But look, when I solve this, the sum of the forces equals ma in the x direction. The acceleration is 0. right? So that says all my forces must equal 0. So look what happens. Here's my x component, here's my y component, which you can use your theta to figure out what those are, right? But if I just say, look, I've got Tx going to the left, and I've got horizontal force going to the left, and they must add up to be 0. So what does that mean? That means Tx equals negative h, or h equals negative Tx. What does that mean? That means that my h has to be a negative force. So if you come up with one of these, because it's a little more complicated than this, and you end up picking a direction that's wrong, your answer is going to end up to be negative. And if your answer is negative, no big deal. You say, uh-oh, what I did is I just drew it in the wrong direction. It's actually this way.
No, it's okay.
And it's no big deal.
Can we do that every time?
Actually, yes.
I wish it was all that simple.
Do you remember when I talked to you last time about those bridge problems?
Suspension bridge?
Sorry.
Ah,
We had cars on the bridge.
Those cars are really big compared to.
Yes, they're very big. Very great bridge. Very big.
Very good.
All right. And we did this. We would take one part of the bridge, say right here, and we'd pull it out, and we'd say, look, we've got an object going this way, this way, this way, and this way. Those are all parts of my bridge. And what we would do is we would pick a direction, and we would randomly pick directions. Okay, I'm going to pick this one to the right, this one down, this one down, this one down. Voila. Now that's not going to be in equilibrium. But we didn't care. Because when we got through, our answer would be positive or negative. And if our answer was positive, we picked right. And if our answer was negative, we picked wrong. And it was in the opposite direction. Voila, we're done. So when we set up our problems, we didn't really care which direction we picked because it didn't matter.
Because you could just switch it.
Because you just switched at the end. Okay? So that made your setup a lot faster because in a problem like this, it's hard for you to know without some experience which way these forces are going to go inside here. So you didn't care. You just set it up, and when you popped it all into a huge matrix and solved it, your answers would come out as positive or negative, and then you just go through and change the directions of your arrows. That's it. All right, so 13 and 14, don't worry too much. You just got to pick your directions. Actually, 13, 14, 15, you have to find tension and the two components at the pivot. All right? Okay, let's go back to this one right here.
Yay.
Orange sheet of paper. The ladder against the wall problem. Okay, you've got a wall, you've got the floor, you've got a ladder sitting against the wall. Okay? You're standing on the ladder, or the ladder itself has mass. So you've got an mg this way. All right. You've got reaction forces here and here. First of all, let's handle the normal forces. Which way is the normal force here going to have to point?
to the right.
Yeah, it's probably a good bet that it's pointing to the right. We call that normal number 1. How about the normal force down here? Up. Okay, that's probably a pretty good bet there. Normal force number 2. All right, it says the wall is frictionless. Let's forget about the wall for a second. It says the floor is not frictionless. Because if the floor is not frictionless, what's this going to do? It's going to slide right out. All right? That's why they have a nice sticky pad on the bottom of nice modern ladders so that they don't slide out. Because it's a very frightening sight to see a ladder sliding out with somebody on it.
That does sound pretty scary.
It's pretty scary to watch. You're like, no, I'm not just seeing that, am I? And you're watching the person slide down the wall.
Have you seen this?
They put it on America's Funniest Home Videos.
Yeah. I saw a video of it. I didn't see it in person. I saw the video and I'm like, oh no!
Watch out.
Yeah, it's like you're watching it in slow motion going, all right, there's nothing I can do. You know? All right.
Sit back and forth.
Yeah, sit back and get some pop. Okay, which way is friction?
To the left.
To the left, to the
It
Wants to slide back.
all right, it wants to slide that way, so friction is this way.
It's all balanced.
All right, if there was friction on the wall, which way would friction be?
Uh,
Yeah, because it wants to slide down, right? There you go. So the friction force would be up from the wall. Okay, there you go. That's the end of our lovely orange sheet of paper. Yes? Yes. All right, e-homework number 1.
Yeah, number one, yeah.
Oh, come on. It's not that hard.
It's awful.
I got 2 through 9, but not number 1.
You know what, man? Well,
And no, number 2 is Captain. Look at it. It's a stick figure. How bad can it be?
I don't know, I haven't seen it. I'll see it. I'll look at it later and try it. I won't cry.
Well, if it's at point A, then you just do it from here, right?
All right, everyone. Key thing here is to draw your free body diagram properly.
If I can draw this, I'll be in trouble.
Wow. But only with that.
Right?
Draw things.
Okay. All they're asking is, what's that mass M? To keep the car from going anywhere. It's static. It's not even accelerating. How hard can it be?
There's super friction on the thing, therefore.
There's no super friction.
Super.
Bad. No super friction.
That's creative, Mr. Bruin.
Okay.
The car is really a
I suggest you draw this free body diagram right here. This part right here.
Here.
And this part right.
You forget there's 2
Here.
pulleys in that big circle.
I don't forget nothing. Me forget nothing. So look at this. Here you go. Here's my car. How many forces act on this car pulley over here?
Mini.
I got an MG.
Normal.
I got a normal force.
Got a tension.
A tension?
2 tensions.
Why 2? Because the tension pulls twice. Because for the pulley. So I've got a tension and a tension. There you go.
I guess
There's no friction.
I guess I still don't believe that pulleys do that.
You better start believing.
All right. Did they give you a coefficient of friction? Then you better assume it's frictional.
It says assume all.
Don't make it harder than it has to be. Do they tell you anything about the drag coefficient? So you don't do drag either. Well, plus it's not moving. All right, here's my other one. Okay, right here. I've got a MG here, and I've got a tension here.
Why is it?
Oh, bummer.
See, you did forget.
Drat, shut up. I've got tension here, and I've got an MG here. Just checking to make sure you're paying attention. That's all, really. You see this? Is this a torque problem over here?
No.
Over here, is this a torque problem?
Yes.
Okay, so sum of the torques equals 0 here. Notice you have 2 different radii. Now, you see this tension is at an angle? Does that mean when you find the torque for this tension, that when you solve radius F sine theta, that there's going to be an angle? Okay, everybody watch. This is very, very important because students get decoyed by this at first. My radius is here. Notice that's at a right angle. My radius is here to this one. That's at a right angle. Okay, so in both cases, here and here, this is 1, sine of 90, okay? When you have a pulley and your string is coming perpendicular off with the radius, perpendicular to the radius off the pulley, then that sine theta disappears to a 1. Okay, over here, this is the sum of the forces in this direction, the parallel direction, equals 0. Okay, knowing those 2 things, solving this and solving this, you ought to be able to figure out what the mass M right here has to be.
Could you write it off? Yeah,
7 is a nice, interesting problem, and this is going to come in handy for us later. So here we go. We've got some kind of wall, and then we have this ball attached to the wall. Okay?
Really hard. Like, the walls were in the bridge, you have to find it.
All right, they have it like this.
Don't be crazy. He's only touching one break.
They have a string attached to this ball, this sphere, that attaches right here and goes off this way. And they give you this angle theta, and that's it. And they give you the mass of the ball and the radius. So you know the radius, you know the mass, you know theta, you are looking for t.
You're looking for, you're supposed to make the torque equation and then kind of deduce something from it.
Okay, they do give you that there's friction. Okay, first of all, let's draw a free body diagram. We have tension already. What other forces act on this object?
Right?
Okay, there is a weight or gravity force,
And friction.
and there's a normal force, which would be, that's very important we draw them exactly where they occur, because it's a torque problem. So where's normal?
Right there.
Pointing which way?
Left.
Okay, now I'm going to draw it, a lot of you will draw it this way.
Okay.
That's fine. I'm going to draw it over here to show you something. Notice it passes through the center of mass. Okay?
So the torque from that is
Well, I didn't say that yet, but if you would pick this as your pivot point, notice that mg and n would go away.
Let's do it.
Let's do that.
We have another force. We have friction. Which way is friction?
Because
Okay.
if it's tension,
Which way is the ball trying to slide against the wall? It's trying to unroll this way, right?
Yes.
So it's going to try and roll this way down the wall. It's not going to try and slide up the wall. It's going to try and slide down the wall. So friction is
because
right
of the
here.
tension is how I.
Now I'm going to erase this part of the wall so you can just see it. There's force friction. Actually, they give friction the name script F, so let's draw it the same way they do. So it looks like that. So we have these.
Well, then mg should be
Oh, I'm sorry. They do W, right?
and tension is F.
What?
Tension is F. Why would they do that?
All right, let's do it the way they do it, because sometimes a book or the AP test or e-homework gives us symbols that we're not familiar with. They just are different names for the same thing, right? Okay, what are they asking for? First of all, to do the torque equation about which point?
O, which is the center of the sphere.
Okay, write the torque equation about the center of the sphere. Center of the sphere. Center of the sphere. Will you do that for me, please?
How?
How?
What?
Here.
Still have that whole spirit.
Here, Andy. I'll help you. Right here. See right there? Right there? Voila. Does that help?
No.
That's your pivot.
Excellent.
It's not your normal go away, Andy.
Okay.
Why did they go away?
It's
Where
still
did they go?
sphere.
How many torques do I have? What's the? Do I have torque from the weight?
No.
Do I have torque from the normal?
Because it passes through the center.
No, it goes to
What's its radius?
pivot.
Not from normal. Do I have torque from friction?
Yes.
Yes.
Do I have torque from force F?
Yes.
So the sum of the torques equals what? Zero. Is F producing a positive or negative torque?
A negative.
Negative torque. This is producing a positive torque. So I'm going to say that, ooh, what's my radius to this one? R F sine theta
No.
equals R F sine theta.
don't mess
The theta in the friction, isn't that equal?
Theta equals.
There you
90
go.
above K.
Sine of what angle?
90.
90. So which is 1. Over here, here's my radius.
90.
Sine of 90, which is 1. Voila, voila, voila.
No way.
Way.
Yes.
Do I look serious?
What's your ruin?
Is that a real question?
I'm
Yeah.
so confused about the whole friction. Why is it up and not down?
It has to be up from our torque equation because it has to balance out. If the force was down, then I'd have two torques trying to roll it. Also, another one is that the ball is here. It's being held like
I
this
got that wrong.
against a wall. It's trying to slide this way against the wall down and not slide this way up against the wall. Okay?
Back.
All right.
Just because I
Custodian can scoop you up.
So I had number 7.
Now, once you find that, you can probably use just your regular X forces canceling and your Y forces canceling to find out what W and N and F and friction are. Okay? There you go. Number 10 is a problem where you have a box or a block or something, you're giving it a push right here, force, and you're trying to tip the thing over. Now remember, when you're tipping this thing over, there's going to be 4 forces. There's an mg. There's going to be friction this way along the surface. And then there's also going to be a normal force. But the normal force is going to be concentrated right here when you're pivoting the box at that point. Because once you get it up on that edge, the normal force is all on that edge. Okay? And if that's like a cardboard box with a lot of junk in it, that edge will start to crumble, right? Because all that force is right there on that edge. Okay? So you're trying to tip it over there. So your natural pivot point is right here. But you're right at the spot where you're trying to figure out the point where it begins to tip. Now, I'll tell you again, in this one, I erased them all. You can still see them. Torque equals R cross F, torque equals F, RF sine theta, torque equals R times force perpendicular, or torque equals the perpendicular radius times the force. It's one like this where it's easy to figure out the perpendicular radius. Here's my perpendicular radius to this force. And here is my perpendicular radius to that force, right? Nice and simple. Some problems, the perpendicular radius is nice and easy to find. So you use that instead of finding the perpendicular component of the force. Okay? If you know the geometry of the problem, a lot of times using the minimum perpendicular radius is the easiest thing to do to find your torque. Okay? What we talked about so far is if it's static. And we've talked about the implications for torque if it's static. You can pick any pivot points you wish if it's not rotating. Because if it's not rotating about the real pivot point, then it's not rotating about any pivot point. So you can pick any pivot point you want. All the torques will always cancel. Okay. Now, what if there is a real pivot point? What if it's no longer static?
You mean, what if it's actually pivoting on this thing?
Yes.
Bianca.
What if it's actually pivoting about the pivot point? Oh my goodness. We're going into the world of rotation.
Things don't.
Nothing rotates because it's all on the board, right?
Exactly.
All right. Let's say that we have a pivot point here. We have a little little metal rod or something here, and we have a little rocket ship. Okay. Here's my little rocket ship. My little rocket ship is
holding it there.
Is attached. It's at an angle, and so it's exerting a force this way. All right. Is all that force causing it to rotate?
No.
No. So we split that up into 2 components. The force that's parallel to the radius, and here's my radius, and the force that's perpendicular to the radius. Okay? All right? Only my perpendicular force is causing torque. So here you go. The sum of the torques. Now let's do this. I'm going to write this. F equals ma. and I'll get to torque. Now, I will warn you in advance, this is not a proper derivation. Okay? All right? My perpendicular part of my force will cause me to accelerate in the perpendicular direction. Or I should write tangential. Do you prefer that?
No. That's fine.
Oh, you like that. Come on. All right. But what is my tangential acceleration?
Change in velocity.
No, it's omega times r, right?
Sure.
Yes.
Tangential acceleration.
What? I thought that was
Oh.
velocity.
Thank you, Mr. Bruin. I'm not crazy.
What is it really then?
Alpha R.
No.
V squared.
Okay. My
Omega
tangential
squared R.
acceleration, remember there's two types of acceleration, right?
The
It's
square
a
root
change
of
in velocity
a
over
squared
change in
times.
Which accelerations will I have over here? I'm going to have a
cent-
centripetal, and I'm going to have a tangential, right?
And then you have your actual.
Now, this one is v squared over r, or omega squared r, right? What's this one going to be?
Change in velocity.
Yeah, it's change in velocity or change in time. Or I could write it this way.
dV.
I could write alpha times r, right? Everybody okay with that? Is mathematically that correct?
I don't know.
Yes. Sometimes.
I
Yes.
thought.
I can't.
I suppose.
With that, I'm going to plug it in. So I get this.
We'll go raise this one.
All right?
We only want R.
Okay, is it okay? Radius cross force equals torque, right?
Yes.
Okay, so I'm going to do a little fancy footwork here. I'm going to multiply both sides by r.
Okay.
Nothing fancy, but R squared.
So this becomes torque, right?
Fancy.
Yes.
And this becomes mr squared times alpha.
Yes.
Okay? The direction of my torque is going to be the direction of my angular acceleration, correct?
Yes.
I suppose.
If I torque it this way, it's going to angularly accelerate this
Out
way.
of the paper.
Yes, if the torque is this way, then the angular acceleration is this way. Right?
So the angular acceleration vector.
That's right.
Thank you.
Very nice, Bianca. Very nice. Okay, everyone, we give this a name. That name is I.
I.
Yes, I equals
Don't like
moment
this.
of inertia.
Wait, is this the incorrect derivation?
Yeah, this is the incorrect derivation
What's
to get to
incorrect
this.
about it?
The fact that I didn't use calculus.
You skipped over the calculus part?
What calculus?
Okay. That's fine.
I kind of backhanded our way to this, okay?
But this
All right,
is-
here's the deal. If there's a force, there's going to be acceleration, right? But if there's a torque, there's going to be an angular acceleration. The angular equivalent of force is torque. The angular equivalent of acceleration is angular acceleration. The rotational or angular equivalent of mass is rotational mass. Rotational mass, they give it this name of moment of inertia. Think of it as
Rotational mass.
it's rotational mass.
Just a second.
It's the mass, it's the inertia you experience when you try to rotate something. Okay, now if you try to push something, you know whether it has a lot of mass or not because of its inertia, its resistance to changes in motion, right? If you try to rotate something, it's the same way. If you try to rotate something, if it has a big moment of inertia or rotational mass, then it's going to be harder to rotate. If it has a smaller rotational mass, then it's going to have less resistance to what you're trying to do to it. It's going to rotate easier. So let's look. What does moment of inertia consist of? It consists of mass and
Radius.
where it's located, the radius of that mass. Okay?
So,
So is it possible to have something that has the same mass, two things to have the same exact mass but have different moment of inertia?
Yes.
You bet. Okay? You bet. Gymnasts and divers in the Olympics take advantage of this.
When they curl it up,
Yes. When they want to spin fast, what do?
they tuck.
They tuck. Their mass hasn't changed, but they've decreased their moment of inertia so that they can spin faster. What did they change?
Oh, right.
They changed their radius, right? They've changed the radius of the mass. And all they've done is make the mass more compact, so it has less of a radius, therefore it is easier to rotate it.
LED lights.
If you don't believe that, try to do a backflip. Okay, anybody ever done a backflip? Anyone? Anyone? Excellent. When you do a backflip, what do? Go like this, and then you jump up, and then you tuck. Right, you pull your legs in. Because if you don't pull your legs in, what do?
You fall on your face.
Yeah,
It depends.
yeah, it depends, but it won't be good, no matter what.
And then you can throw yourself out if you want to. But that's only if you can.
Oh yeah, if you're really good, you'll tuck a little bit, and then you'll throw yourself out and then land. But that's only if you're really
If you're high
strong.
enough, then
Yeah,
you
you
can
got-
like X out of it. But if you're like barely skinny over the floor,
Yeah, you
gently
keep tucked.
on the floor.
Yeah, that's exactly right. You'll see people do this off like a diving board at the pool when they try to like do a little turn and they'll end up like on their back or on their face or whatever. Yeah.
I can't really picture it.
Have you had this?
yeah.
Anybody? Can anybody still do a backflip?
Alex.
We're so old.
This could be scary.
Are you really going to ask her to demonstrate
Can you really
a
do it?
backflip on this floor?
Or no, it's just sick, right?
All right, I don't want you
There's
to.
nothing wrong. Well, there's something wrong, but she's like, I don't know.
Oh wait a minute, you got a headache. Don't do it.
No,
I don't want your head to
I
explode.
don't know. It's like, it's fine.
It's only a sharp digging pain right here.
I have that right here. It's so weird.
I'll do it.
All right, we'll do it next time. All right, practice. Go home. That's your homework. Do backflips.
So I don't have
Come
to
in.
eat homework.
If she doesn't come back, we know what happened.
Mr. Bruin.
I learned how to
And
do
then if it's
backflips.
recorded, you can do it frame by frame.
That's right. We
Talking
can
about
we
the-
can do it. We can slow it
It
down.
could be a lab for the super class.
That's right.
We calculated
And
her
if you-
rotational.
Can you like run and do a flip and then land on your feet running? Because if so, we can show you that your center of mass does a parabolic motion.
So, Mr. Bruin, if you look at something spinning, like continue perpetually, can you tell its center of mass
Yes.
pretty easily?
Yeah. An object will rotate about its own center of mass. In fact, that was the next thing we're going to talk about.
Okay.
All right. So here you go. Now, next thing we have to talk about is when we're talking about moment of inertia. Before we get into calculating moment of inertia, the very first thing we have to do is figure out where the center of mass of an object is and what the center of mass is. Does anybody know what center mass is? What's center mass?
Where you rotate around.
Yeah, it'll be the spot of which you'll spin around, but if you like fly through the air, so like if we take you and throw you across the room and you flail around, all parts of you will be flailing around except your one spot, which is your center of mass, which will do this. A nice parabola.
It'll be the real.
So like, here's you flailing.
Wow. I'm
All right,
spinning out really
but your
fast.
center of mass will stay the same spot the whole time. Your center of mass is the spot that goes right here through the air in a nice parabolic arc. Okay, the symbol for center of mass is this. Looks like the BMW symbol. Okay?
Except in that case.
Yes. All right? And center of mass is important for us because center of mass tells us a couple things. Number one is if an object is in free rotation, it will rotate about its center of mass. And the other thing is it shows us where we place the weight force, the gravity force. The gravity force is always drawn from the center of mass. Okay? Now, if you go further into science, what you'll do is you'll distribute it out. But for us at this point, we're going to have it all centered at the center of mass. Okay, so how do I find the center of mass of this thing?
You
Throw it.
throw it across the room.
I could throw it across the room, spinning, videotape it, see what point it's rotating about, and that's the center of mass.
Can I like balance it?
You could balance it. Here, can you balance it?
I can.
Someone's going to be a future genius. Balancing.
Somewhere. No, he passed the 8.
Whoa, he found it.
It's somewhere there ish.
Nice. Okay.
I think I'm effective.
Okay, so it's right here. All right? Now there's another way to find it. Balancing it sometimes is not real practical, like finding your center of mass. Yeah.
Balance me.
Balancing you, yeah.
But like if you have those cool
Oh, it's like if you
dove
take a
things.
baby. I know this sounds bad, but like if you want to feed,
Take a baby,
they
throw
like
it.
stand up and like, and you have to like, I don't know if you've seen that.
Yes.
They hold the feet and they're like, oh, how you doing? Just like, yay.
Yeah, I've seen that. Another way to do it is to do this.
That's
If you just
it.
hang it from a point like this, the center of mass will be directly where I'm hanging it. Why?
Because of the
Because of gravity. Boo! Bad answer.
weight.
Because the center of
Because if the center of mass we said was right around here, actually here, we said it was right around here, okay? If I have it like this, I have a force up and a force down, which produces a torque
Yeah.
this way. And if I have it over here, it produces a torque this way. But if they're directly above and below each other,
it's static.
static and no rotation. So it's going to be directly down here. So you draw a vertical line here,
Hold it.
draw a vertical line here,
Intersection.
draw a vertical line here, or anywhere. You can hold it anywhere and draw a vertical line. Where the vertical lines cross is the center of mass.
So
Okay.
we can hang someone on the wall. and
That's
say-
correct. So you hang someone by their arm, and hang someone by their neck, draw two vertical lines.
Oh, okay. We're just finding your center of mass. It's okay.
We're just
You died for this subject.
Yeah, but now if you change your position of your arms, your center of mass changes. Like for instance, where's my center of mass right now for me?
That's how you squeeze.
Now for guys, it's up here a little bit farther because guys have more upper body mass. And for girls, it's a little lower. Okay? Because girls have less upper body mass. Okay, now wait a minute. Watch. Whoa, where's my center of mass now? Whoa. Where's my center of mass now?
At your,
It's in there where it's like in that.
It's right here. Right here.
It's where your tie is.
It's right here.
It doesn't have to be part of it. What
Okay.
if it didn't have the
Didn't have to.
That's right. Okay, now, your center of mass does not have to be on the object.
So if you didn't have your tie on, it would still be like that little
Yes.
visible point right there?
Now look, my center of mass has to be directly over my footprint. Does that make sense?
No.
Because if my center of mass is off of my footprint, what do?
you're opening.
I fall over. So why is it more stable to stand like this than this?
Because you're opening up.
Because now, you got to really push me over to knock me over, right? To get my center of mass over the pivot point,
You have to push farther.
you have to push farther, right? Okay, now look, when I stand like this, see where my footprint is? My center of mass has to be above that, right? Or otherwise I'd fall over, right? Does that make sense?
Oh, that's crazy. Get off my center of mass.
That's right. I'm tired of my center of mass being on me. Okay, where's the center of mass of this?
That should be a movie.
In this
Running away from your
Right
center.
here. Alright, so the center of mass does not have to be on the object. And here's the crazy thing. So like for instance, if we had an object like that, like if you had an object like the letter C, and you were trying to draw like a free body diagram of this thing,
I throw the letter C at someone.
See, throw the letters.
everyone, shh. That's where you draw its weight.
That's cool. Company.
Okay? That's where the weight would be concentrated mathematically at that point.
If they wouldn't tell us where the center of mass is.
Oh, so they don't tell us where the center of mass is.
For what problem?
Let's find it.
We're good at this segue thing.
I
It's a
think,
smooth
Segue is
transition.
the word.
I think we should.
Yes,
go to the
you are
office
good
and
at
have,
segue today because you're asking just the right questions at the right time.
Mr. Bruin, the
Center of mass.
Can't be home, I'm glad.
Yes.
what
one second.
would be this? The mass center of mass would be located at a radius.
No, but tell me.
What center point?
Here. Here's how you find the center of mass. The x dimension of the center of mass is equal to, here you go, here's the calculus version.
Yay.
Okay.
Okay, what's this?
Mass.
That's the mass. Okay?
That's the mass distance.
This is the distances of all the mass parts. The sum of the mass times their location summed up. Now, in summation form, it looks like this. The sum of the x m's, okay, over the sum of the m's. So like for instance, let's say I have an object like this. That's 3m here, and then it's m here, and the distance from here to here is x. Where's the center of mass? Okay, now, it's not going to be in the center. It's going to be more to the left. You need to pick a coordinate spot where you're going to begin. I choose this spot right here. I choose that as my distance spot to measure from. When I do my sum of my xm's over the sum of my m's, well, the sum of the m's is easy. That's just going to be 4m. But the sum of my xm's is going to be distance from that spot in the x direction times the mass. So I'm going to get 0 times 3m plus x times m. Does everybody see the 0 times 3m? And so I end up with xm over 4m. So it's x over 4. So it's 1/4 of the distance over. Right here is the center mass. See how that works? Now what if you have an object that is a lot more substantial? Say you have an object that looks like this. That's 3m and 2m and m. First of all, where will the center of mass be?
Upper left.
It's going to be more up this way. Well, wait a minute. I got 3m here and I got m here, right? So won't it be like right here? Somewhere in here?
What's the?
But it's going to be more this way, right?
Yeah.
So it's going to be somewhere over in here probably. All right. So if this is x and this is x and this is x, and I want, if this is my xy coordinate system, I want to find the xy coordinate of where it is.
Okay.
All right? So let's do that.
You're gonna use sign.
X center of mass equals the sum of my xm's over the sum of my m's. Well, the sum of my m's is going to be 6m. All right.
Thank you.
This one right here, that's going to be 0 times 2m. I'm just doing that to remind you that it's there, but it has no radius, right? Okay, and this one's going to be plus x times m. Plus, okay, how far is this over? Yeah, that's going to be x over 2 times 3m, right? So what does that become? I get xm plus 3 over 2xm over 6m. My m's go away, right? So I end up with, what, 5 halves x over 6, right? Which is 5/12 x. Does that seem right?
Yeah.
It's a little bit to the left, correct?
Yes.
Okay, so that seems okay. So it's going to be somewhere over here. All right, now let's do the vertical part. Y, center of mass, equals the sum of my ym's over the sum of my m's. Okay, the sum of my ym's. Well, I'm going to get 0 times 2m plus 0 times m plus, what's this?
Square root of 3 over 2.
Square root of 3 over 2, 3m over 6m. Okay, well that goes away and that goes away. So I end up with square root of 3 times 3 over 2 divided by 6, and my m's go away. Ugh. So that is square root of 3 over, or times 3 over 12. So that's square root of 3 times, or over 4. I thought it was going to be in the center. Well, wait a minute, that still might be in the center. Square root of 3 over 4.
And the height is square root of 3 over 2.
Yeah, that's right. So this is this is the square root of, this is 1/2 x, right? X over 2. So this is x square root of 3x over 2. So yeah, it's square root of x through square root of 3x over 4. I lost my x somewhere.
Yeah, I know. I was like, wait.
Where did I lose my x? I made a mistake.
Write it all down.
Oh, it's right here.
You didn't write it, yeah.
It's just supposed to be x in here, right?
Where did I lose my X?
X, X. There we go. Come on, you're supposed to pay attention and keep me from mistakes.
Yeah.
This is on video. I look stupid.
Or was that on purpose?
No, that one was not on purpose. That was really bad. All right, that's how you find your center of mass, okay?
Sometimes.
Cool.
Okay, now, center of mass is going to be really important when we get to momentum. We're going to find out that in a momentum collision, that the center of mass, its motion never changes. It's the velocity of the center of mass remains constant. So like in a collision when things collide, the center of mass of the system never changes. It just keeps going. It's crazy.
It just like passes through, like,
Oh, that's awesome.
like as the mass changes.
Yes, it's really
It
nice.
makes so much
It's
sense.
based on conservation.
So when
Yeah.
you die,
What we find is that the sum of the MVs over M never changes.
your center of mass doesn't have to be within you.
All right.
I don't think you're so.
Now, next time, we're almost out of time. Next time, we're almost out of time. We are going to be a day behind because next week we're going to lose a day. So our test, which is scheduled for next Friday, will not be next Friday.
Why are we losing?
And we're all PSAT. And we're also going to be, we're also a little bit behind anyway. Next time, everybody, bring your calculus heads. Because we're going to figure out what moment of inertia is.
I'll bring
Moment of
pocket
inertia
trivia.
is the integral
Pocket trivia.
of the r squared dm's. Remember we said that moment of inertia is r squared m, or mr squared? Okay. That's how we calculate it with calculus.
I am squared.
Yeah.